Hello, and welcome to our third webinar, the third webinar in our Syft series. With me today is my colleague Mads. And as usual, if you have any questions during the webinar, just write them in the chat and we'll take them in the end. I'll just share my screen and make a pointer. There we are. And I just did this presentation in Danish, that's why we're at the end already. But as usual, we are talking about the Syft MS. And yeah, a little bit about Mads, since he haven't been here the other times. He's an engineer from the Technical University of Denmark. And yeah, the rest you've heard already from that. Today we'll talk about primarily some applications, so very shortly about what is a Syft MS, and then some interesting applications I've found. Mobile environment analysis, multiple headspace extraction, a bit of scan PCA data, some scan environmental analysis, and BTEX in soil. So when I talk about the Syft MS, I'm talking about the Voice 200 Ultra, which is the newest instrument from Syft Technologies. It's select and flow tube mass spectrometry, and it works as a direct mass spectrometer without the chromatography. But since it doesn't have chromatography, it needs to differentiate compounds in a different way, and it's using ion chemistry for this. The major advantage of the Syft MS is that it is really fast analysis, and it's designed mainly for targeted analysis. And another benefit is that it has high sensitivity, so it can detect compounds at a very low concentration of around 1 ppb volume, and it has a wide linear range, so while you're detecting stuff at 10 ppbs, you can also detect other compounds at the low ppm levels without any problems, as long as they don't share ions, of course. It works by having a microwave plasma that makes ions from atmospheric air. Then you have the quadrupole for selecting the ions you want to react with your analytes in the flow tube. Then you have the quadrupole to differentiate the product ions and the particle multiplier to amplify the signal. And then we'll get into some of the interesting applications I've found. The first one is that there are a few people or a few groups that has made mobile environmental analysis using the Syft MS. And the reason that this is possible is because it has this fast analysis time, so you can drive around in a car and get data points every few seconds, and then you can do some interesting stuff with that. The reason this is even possible is because the Syft MS is designed to be a robust instrument, so it can handle somewhat rough handling. But still, when you're driving in a car with it while it's running, you do need some kind of extra suspension, and as you can see, it's in this picture, it's in an extra box to, for instance, if you're driving over bumps in the road and stuff like that, to steady it. And yeah, another reason that it's possible is that it is a mobile instrument. Even though it's 200 kilograms, you can relatively easily roll it around and get it into a car if you have a proper platform for it. The left one is the kiosk version of the mobile, while the right one is the one from University of York. And as you can see, this is from Korea, where they have a lot of these cars driving around doing analysis. So the first set of data from such a mobile laboratory is from KIOST, Korean Institute of Ocean Science and Technology, where they've been driving around measuring different compounds. And this example, they have taken out the data from benzene and plotted it. And here you can see that in some areas there's really low signals, while in others there's a very high signal of benzene. And this is again possible because it does this very fast analysis, so you can drive through and then you have a set of data for that road. But another reason that I included this one is actually just because I'm very much a fan of how they've made this plot. But what you can use this data for is then you know where you should focus your efforts if you want to reduce the pollution in your city. Another example of mobile environmental analysis is the University of York, who drove around in York measuring NOx gases, SOx gases, and other pollutants. But I'm only taking a curiosity out from this work done by Rebecca Wagner. And that is that one of the things they analyzed for was acetone. And a funny detail is that if you look up here, that's a street called Gilgate, and there they found the highest concentration of acetone of anywhere. And that was a bit curious, so they went back to the street and looked further into it. They then had a student try to put some thermal desorption tubes into they found out there were a lot of nail salons on that street, and that was the reason for the high acetone level. And they confirmed this by having a student putting some thermal desorption tubes into the different kinds of shops that was on the street and just outside. And here you can see the ratio of the concentrations found just outside and inside. And you can see here the nail salons has 500 times more acetone inside compared to outside, which would make sense when you think about it. But that also means that there's a lot of acetone that can seep out and then be measured by the Syft driving by. Another thing you can use the Syft for is instead of driving around yourself, you can make stations where you measure the pollution from different vehicles. In Denmark, we just added something called environmental zones, where in the center of the city, they take a picture of your license plate, and if it's registered as an old diesel car, you're not allowed to be in the city, and then you will be fined because you are not keeping to that. But another way to do this could actually be also measuring the pollutants. Already some people are doing this with spectroscopy, where they measure the pollutants using a photospectrometer. But you could also do this with a Syft, and a Syft would yield better data, and actually this group at the University of York are trying to do that right now. And then you would actually know what kind of pollutants come from the different cars. The next application I'll get into after I have a drink is multiple headspace extraction. And this is the age-old question. If you have a solid or a liquid sample and you measure the headspace, how much did you actually measure? And how do you even know what's in the sample? One thing you can do is simply to keep analyzing it. You start out, of course, by generating the headspace. Then you measure the headspace. Then you flush the headspace. And then you generate new headspace. And if you do this indefinitely and then add all the concentrations you find, you will end up with the sum of what was in the sample. Luckily, this develops systematically, and you can see here that in the data, you get the concentrations from the first one at the top, and then you get less and less and less. And as you can see, the distance between them is shorter for each time because you have less. So of course you get less in the headspace. And this example is styrene in polystyrene. And as you can see on the left plot, it develops exponentially. And that's fortunate for us because then we can take the normal logarithm on the y scale and get a linear plot. Here you can then use an equation and find out the full concentration. But why am I talking about this when we are talking about the Syft MS? Because you can clearly do this on a GC as well. Well, of course, because the Syft MS is really fast, as I've talked about earlier. If we look at the left, we are analyzing one sample using multiple headspace extraction. Each yellow is the agitation time, the pink is the actual analysis time. And as you can see, there's a lot of wasted analysis time. But you would, if you analyze one sample using multiple headspace extraction, it would take you 1 hour and 50 minutes. However, if you use a Gerstle MPS sampler and analyze 4 samples at the same time, it would only take you 2 hours and 4 minutes. So it's a very minor increase to get 4 times as many samples. And this is possible because the analysis time isn't the limiting factor of this analysis, it's the incubation time primarily. Previously, I've talked about that you could use multivariate statistics to analyze your data that you've obtained from the Syft. And this is just a little example I did. We found out that it's really hard to pipette from a measuring glass. So is it okay to pour it up into a plastic container, or will the plastic container contaminate it? So I tried to run a series of experiments where you either kept it in the glass or you poured it into the container and then pipetted it into a vial later. And what I found out was simply that, of course, this is a PCA plot, and it's essentially you can see our samples different from each other. So you can see here, because all the ethanol ones are on the left side and the water ones are on the right side, then you can see that the difference in PC1 is it water or ethanol. Then in PC2, you can see, okay, we have test, test, reference, 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 test, and the same over here. That essentially means that the test and the reference are not different, statistically different from each other. And what I did was, of course, I measured it on the Syft full scan mode with all 3 ions. So actually from this data, I can't really, only because the water and ethanol tell what's different, but I'd have to dig further into the data to see what's the difference in PC2. But from this, I can conclude that it's safe to use these plastic beakers for pipetting if I'm using ethanol or water. Another example where this could be interesting is for quality control screening. Because if you run quality control of each batch, they will be close to each other in a PCA plot. And then if you then get a different batch that has some significant difference, you don't even need to know what it is, then the mass spectrum will be so different that it's away on the plot, on the PCA plot. And then you can look further into it using, for instance, GCMS. Another example of using scan data is that in this other example of using scan data, they placed a Syft in a school which was adjacent to an industrial area. Once again, they measured the full scan, and then afterwards they made a method for 48 different compounds that have previously been identified by GCMS, thermal desorption GCMS. And because the Syft is so fast, you can get a time resolution which just isn't viable with using thermal desorption. Because you usually place out your tube and wait for many hours, where here each data point is a short period of time. And then you can, for instance, try to correlate the higher concentrations with processes happening in the industrial area. So for instance, if they're unloading something while in these times, then it might be related to the methanol levels that are higher. And of course, there's some, when you're doing environmental analysis of air, wind is always a factor that you have to keep in mind. But yeah, that could essentially be used for maybe if unloading this causes high release of methanol, then it might be a good idea. What? Okay. It was just my colleague who thought I'd lost my sound. But essentially, if you're unloading something that gives higher levels of methanol, it might be a good idea to, if it's possible, to move those processes. So the next application that's interesting is methanolic extraction of soil in BTEX compounds, where this is actually one of the places that's brilliant between the Gerstle MPS and the Syft MS. Because the last step is measuring headspace, and the Syft is really good for that. You can also do it with GCMS, but once again, the Syft is fast. So you can run more samples if you're using a Syft MS for this. The only manual work you have to do for this is that you have to fill up a rack with 10 milliliters of sodium chloride solution, and you have to weigh off your 2 grams of soil that you want to analyze and put in a different rack. And then you can make the Gerstle MPS do all the rest. You can add the methanol, you can sonicate, you can centrifuge, you can move 250 microliters from the extract to the sodium chloride. You can incubate it and tell it to inject in the analysis. Last time I talked about the reagent ion depletion, and that you generally shouldn't use organic compounds for this using analysis by Syft MS, because it will consume all the reagent ions. But it's actually possible to do this analysis because of the reaction rate of methanol with NO+. So here you can select a specific reagent ion that reacts very slowly with methanol. That means that it doesn't really consume all the methanol doesn't really consume all the reagent ions, and you can analyze the other things when you use NO+. In this work, they also check all the analytical parameters, such as limit of quantification. They just did a 10 ppb sample because that's plenty for the application, and you can see that there's a clear signal compared to the background, which is essentially 0. Then there's the linearity for the different compounds, just the standards, and it's really good with an R squared of 0.99, and in most cases another 9. Then they measured the instrument precision, still with standards, and the best they got was 1 1.2%, while the worst is 5.6%. So that's also a really nice precision. Sorry. And then they bought some standard soils from a chemical supplier and tried analyzing them. And the analytical precision they got was still as good and actually better than just running the standards. Lastly, they did a spike experiment in the different soils and measured the recovery. And generally, they got a recovery plus minus 20%, which is still very good for this kind of analysis. They also did with the 2 other different kinds of soil, but it was basically just the same data. And if you want to see these applications more in detail, they are all on the Syft homepage under webinars. And that was actually all I had for today.